Okay, so last time we looked at this equation and we saw that it resulted in this graph. So the equation up there and the graph are mathematically the same because they both represent something. What is it? Talk to the person next to you. Why are those mathematically the same? Not just so what students often think is these equations then becomes like the name of that curve or the label for that curve. Like we're putting that in and graphic calculator is going into its memory banks and finding that picture whose name is that. It's not what it is at all. These are mathematically equivalent. So have a short conversation. How is that equation mathematically equivalent to that curve? Go. Okay, so what do both of those represent? Both the equation and the graph represent the same thing. So in a nutshell, what do they both represent? What's that? 7 is the output. Not quite.
X and Y values both on the line and that satisfy the equation.
Right, a set of ordered pairs, X and Y. So if you said something like that, you got it right. So they both represent some set of ordered pairs. Well, how does the set of ordered pairs relate to the equation? They make it true. If you plugged in a coordinated pair of X and Y into that equation, the left side would equal 7. Okay? So they make that true. And then how do these set of ordered pairs relate to the graph? How do the set of ordered pairs relate to the graph? I thought that would be the easier one.
It is a graph.
Well, how is it the graph? How is the set of ordered pairs the graph?
So there are different points that look at the equation.
Right?
So the set of X and Y.
Right, so it's the set of points, right? When you look at a curve, again, your brain should be thinking, oh, that's like a zillion points. All right, and so when this set of ordered pairs is plotted, we get all the points that make that curve. Okay. Question. Does this set of ordered pairs represent y as a function of x? Okay, and what are you looking at to answer that? Yeah, so given any x value, do we get just one corresponding y? There's some places we don't, like for instance here at 3. For this x value of 3, we get one y value here, and one y value up here, and another y value down here. And maybe if we zoomed out, we'd get even more. Okay, so maybe we'll curve back around again, who knows? Okay, so it does not represent y as a function of x. Is it valid to talk about the rate of change of y with respect to x? So we'll talk about that later. So is it valid? So y is not a function of x, but is it valid to talk about the rate of change of y with respect to x? So say I pick a point right here. Is it valid to talk about how fast y is changing for a small change in x? At that point that I showed you. Sure. What about at this point? Is it valid right there to talk about how much y changes for a change in x? What about here? Sure. Yeah, if you pick any point on the curve, you can talk about change x a little bit and see what y does. And we know that change in y divided by the relative size of change in y to change in x would be our rate of change. Okay? So yes, so even though y is not a function of x, we can still consider any point on there and talk about the rate of change, just like we've been doing all semester. find a little change in x. Take a little change in x, look at the corresponding change in y. Set up that ratio of how fast y is changing with respect to x. Okay, is it valid to talk about a rate of change function? Is it valid to talk about a rate of change function? Yes or no? It depends. What about as a function of x? So if x was the input, would the rate of change be a function? No, same thing as before. So if I pick 3, I get 3 rates of change, right? I get the one at the top, the one in the middle, and the one at the bottom. But if we change the input and we think about the input as an ordered pair, so given an ordered pair, do we get 1 rate for every point on the graph? Yes, okay. So we can still think of a rate of change function, but we just have to alter our view of what the input of that is. It can't be just the x value. If the input is an xy ordered pair, then yes, there's 1 rate of change for every x and y taken together, okay? So we want to determine what that rate of change function is. And so in order to determine that rate of change function, we need to, going back to question 1, we need to pretend that y is a function of x. Okay, so we need to pretend, okay? So in other words, y equals f of x is implied, but it does not necessarily exist. For instance, here it does not exist, okay? Y is a function of x. But it's implied, it's kind of hiding in the background, and we pretend that it's there, okay? So this is where the idea of implicit differentiation comes from. That y is a function of x is implied, not in your face, not overt. It's kind of hiding in the background. Because if you look at that equation, what x and y are like tangled together. You can't really solve for y and get all x's on the other side. X and y are they're tied up, they're tangled together. So we just pretend that this function exists, y is a function of x, and that will allow us to calculate this rate of change function. So let's see how that happens. So we start with, this is implicit differentiation, we start with that equation, and the first thing we're going to do is we're going to substitute in for y f of x, because we're going to pretend that y is a function of x. Okay? And so now we're going to then, it's not just y equals x's anymore, so what we need to do is take the derivative of both sides. We take the derivative of both sides with respect to x. So we got this derivative of the whole left equals the derivative with respect to x of 7. And now we've got all the rules. So we're masters or near masters of derivative rules, and we're just going to apply that. So we have the derivative of a sum and difference, which equals what? The derivative of something plus something minus something. How do we take the derivative of that? Each one separately, right? This is the easy rule, right? That if you have a sum or difference, you just differentiate, take the derivative of each one separately. Okay, so we'll do x squared first. Derivative of x squared, 2x. Now we'll go to this. The derivative of a function of x cubed. A derivative of a function of x cubed. What do we need to use? We need the chain rule, right? We need the chain rule. So outer function or external function is 3, so cubed, right? So we're going to use power rule. And what happens on the inside? Remains the same. To the second. Are we done? Times the rate of change of the inner function. So it's for this reason that we need to, every time we see a y, we need to pretend that's a function of x. Because it is some expression of x in a sense, all right? So it depends on x in some way. So we'll just call that a function of x. And that shows us that we need the chain rule whenever we take the derivative of y. Okay? So now we have minus 2x times f of x. How are we going to do that? It's going to be a product rule. Okay? So this is, I want to move down here. So it's going to be minus the first times the derivative of the second, f prime. and we'll put this all in parentheses, plus the second times derivative of the first, which is 2. Did you catch it? So all the same rules apply. If you've got a product of two functions, you need to use the product rule. And now we say equals rate of change of 7 with respect to x. How much does 7 change when x changes? It doesn't, right? So rate of change is 0. It's a constant. Okay, so what are we after? We're after dy dx. We want dy dx equals some expression of x and y. So where in here is dy dx? It's the same as what? F prime, right? So I could have written here, we could have written dy dx, but we were using f of x. Okay, so what we need to do is we need to get this by itself on the left-hand side of the equation, and then everything else over to the right-hand side, so that we can eventually factor out that and get that by itself. So we have 4 terms. The 2 terms that have the f prime x, the dy dx, we're going to leave on the left. Every other term that doesn't have it, we're going to move it over to the right-hand side of the equation. Okay, so we've got 3 f of x squared prime of x. And this will be minus 2x f prime of x equals, so I'm going to move this, I'm going to subtract this from both sides, negative 2x. And then this is actually, see this minus in the product rule comes over here? So that's going to end up being plus 2 f of x. Okay, did I lose anyone? Kind of did a couple steps at once there. Again, we're trying to get a rate of change function. So everything that has f prime, or in other words dy dx, keep it on the left side. Everything that doesn't have it, move it over to the right side. Because now we can factor that out on the left side. F prime. And so we've got 3 f of x squared minus 2x. And that equals minus 2x plus 2 f of x. We got one more step. Okay, if I lost you, do you have a question? Where did I lose you? Anybody? We good? Last step to solve for f prime x is simply divide by this thing that remained when we factored out f prime of x. So it's going to be minus 2x. Okay, plus 2 f of x all over 3 Agree? Did I make a mistake? Follow? If I make a mistake in the algebra, please stop me as soon as I do, if you think I did. Any questions? Okay, but what was f of x in the first place? Yeah, that's what we put that in for y because we just want to make sure we were really cognizant that whenever we saw y, we knew that was a function of x. So we had to treat it as such and use the chain rule. But in reality, that's just y. So we can say minus 2x plus 2y over 3y squared minus 2x. And so what do we have? We have the rate of change, not as a function just of x, but of any ordered pairs, right? Of a corresponding set of x and y together. This fraction will generate the rate of change. So that's also dy dx. So this is, if you want to write as dy dx, that's valid too. Any questions on how I did that? So what does it mean? It means if we plug in an ordered pair that's on that curve into this expression right there, it will give us a number. And that number will be the rate of change of y with respect to x at that point. The same rate of change we've been working on the last month or whatever. Questions? Okay, so let's go to GC and take a look at this. Okay, so I have that in here. Is that the same thing we came up with right there? So I've defined it as r, but now it's an equation of two variables, not just x. We know that in order for us to have exactly one rate of change for every input, that input has to be associated values of x and y taken together. So you do the same thing you would do to define a function with one variable. You just put a comma in there. So I said r control 9 x comma y. And so now it's going to expect, whenever we call upon r, it's going to expect two inputs. Okay, so let's look at let's zoom in a little bit and see if we can get 3 exactly. So this is at this first point when x equals 3. Let's see if I can get it. That's pretty dang close. Okay, so we got this point right here. X equals 3. Y equals 2.2617. Okay, so if I take, that is an ordered pair that satisfies the original equation, and therefore it's a point on the curve. So I can just come here and I can use graphing calculator to tell me what the value of the r function is at this point. So 3, 2.2617. And I get a rate of negative 0.158. According to that rate function that we found. So does it make sense looking at the graph? And why? So why does this rate of change, negative 1.58, make sense looking at the point on the graph 3, 2.2617? That's what our ratio, or that rate of change function gave us at this x and y coordinated pair. So why does that number negative 0.158 make sense? Talk to the person next to you. Okay, so I zoomed in even further. Why did I do that? So now I zoomed way in on this point. What does it have to do with this value, negative 1.58? What's that? Decreasing, okay, so for a positive change in x, y goes down. And we see that how here? Negative, right? It's a negative rate. What about the value 0.158? Okay, so it's small, so what we're seeing is what we're trying to think of here, a severe change in y, severe decrease, or a gentle decrease? It's just a slow, gentle decrease, right? And how could we could take, what? So this is what you should have talked about. We could take a change in x. Here I'm showing a change in x of 0.004. And what then would that change in y be? A couple people out here, a couple who say, you all should be thinking it. That corresponding change in y for that change in x, or how fast y is changing with respect to x. Negative 1.58 times as much as 0.004. So how much that went down would be negative 0.158 times as much as 0.004, representing a slow decrease. Representing a slow decrease. Okay, let's do another. So what if we wanted the equation of this line? So what was that point? It's actually that. What if I wanted to write the equation of this line that had the same slope as the curve at this point, and so that it would be like a tangent line to the curve? How could I do that? I've got this point. And what was this again? Negative 1.58? How could I write the equation of the tangent line? So this is just using something we've learned before. Yeah, we are point slope form, and that's so using a point, given a point and a slope. Remember we built all our piecewise linear functions with this form? So what would m be? Negative 0.158 times x minus 3 plus 2.2618. And yellow won't be good. Let's do something else. Red. Here we go. So I'm going to zoom back out again. It won't lock in here at 3, but you got the point. So that line tangent to the point when x tangent to the curve when x equals 3 at that point. Okay, let's do another example. So here's another one. Cosine of y squared. Okay, can I have your attention, please? Cosine y squared plus x times radical y minus 2 equals natural log of x. Okay, so here's that curve. Actually, there's more to it. Oh, does that impress you? How about this? Okay, but do you know what you're looking at? What are you looking at? It's cool looking, but what does it mean? You're looking at a bunch of points, whether they're on the same curve or on different curves. Every one of those points, what can you say about every one of those points? It's x and y coordinates. Satisfies makes that equation true. Okay, so let's find the rate of change of y with respect to x. So now we won't write f of x every time, but every time we have a y, we're thinking of it. We're pretending that y is f of x. Okay? So we can keep them as y's. It'll save a lot of writing. but we're keeping them as, imagining it's f of x. Okay, so we'll do it over here on the left. So here we go. What's the rate of change of this? It's going to be negative sine of y squared times 2y. So that's a how many? 1, 2, 3 layer chain rule. So y prime, f prime of x, dy dx, all synonymous, okay? By y prime, I mean dy dx, or what we had before, f prime of x. So we did rate of change of the exterior with respect to the interior times rate of change of the interior with respect to the interior times the rate of change in the interior. Okay, what about x radical y? First times rate of change of the second times every time you take the derivative of a y term, you've got to think of that as we were pretending it's a function of x. So by the chain rule, you need to multiply by the rate of change of y with respect to x. Okay? Plus the second times the derivative of the first, which is 1. Derivative of 2 is 0 equals 1 over x. Everything with a y prime is going to stay on the left. Everything that doesn't have a y prime is moving to the right. And then I'm going to also factor out the y prime in the same step. So those two that I've circled in blue stay on the left. Okay, plus 1/2 x equals, okay, I'm not done, guys. Negative y to the 1/2 plus 1 over x. How did I do? Did I make a mistake? Or am I good? So I save the ones that have the rate of change, y prime, and then factor that out. On the left, everything else moves to the right. And then we're ready to divide. So this is y prime, or dy dx, take your pick, equals negative y to the 1/2 plus 1 over x over all this.
Minus y to the negative 1/2, shouldn't that be positive 1/2?
Yeah. So I got it right here, right? Okay, so what do we got? We have a expression now of y and x taken together. And if you pick a point on the curve, an x and y that satisfy this equation, and plug it into that expression will spit out the rate of change of y with respect to x at that point that you picked.